Hello. Today I will show one of the proof by the Greek mathematician named Euclid, who lived around 300 before Christ. Euclid proved that if prime numbers 2, 3, 5, 7, 11, and so on has to be repeated to infinity. He showed us how to prove this. In this video, I will show you later that it is correct that these prime numbers repeat to infinity. The idea is let's make a set of prime numbers P1, P2, P3 to Pn. Let's assume first that this set is finite. It means it has finite numbers of prime numbers. So we need to prove that our conclusion that this set is finite is wrong. There should be another prime outside this set. The idea is, let's imagine a number which is we call P. P is a number that is a multiplication of the prime numbers inside this set to Pn. So P should be larger than P, should be outside this set, maybe here. If we put in this picture, could be here P. Now let's make another number which is larger than P. We say Q equals P plus 1. P plus 1 should be larger than P. Let's put here. Now we have to prove that if there is another prime outside this set, this prime could be Q. Now we have to prove that there should always be prime containing after P, maybe Q or larger than Q. How to prove that? We know that from the fundamental theorem of arithmetic, if a number, a composite number, we know composite number such as 4 is a multiplication of prime numbers. 6, multiplication of 2 times 3. 9, multiplication of 3 times 3. So we know that any number beside the prime number can always be factored into its prime constituents, any number to infinity. Now the same like Q. If Q is a prime number, then our conclusion that this set is finite is wrong, because there is another Q outside this set that says that it is a prime number. So the set of prime numbers is not finite, in this set. Now what happens if the q is not a prime number? How do we prove that there is another prime here? We know from the basic theorem of arithmetic, if a composite number a can be divided by a prime number p, and another composite number b can be divided by the same p prime number, then this is correct. B minus a can also be divided by p, where b is larger than a. This should be correct. Then we apply this to p and q. If q is larger than p and p can be divided by, can always, because p is a composite number made by multiplication of these prime numbers, then p can always be divided by the elements in the set. Let's say p1 or p2. Let's put here p1. Because q is not a prime, q is not a prime number, q should always be divided by a prime number. Now we have to prove that this prime number that can divide q does not contain in this set. That will prove that there is another prime number outside this set. How to prove this? Now let's make a subtraction. We need to prove this statement. If q minus p can be divided, if we assume first that q, there is no another prime number outside this set, then this p should always in this set. So when we say that p can be divided by p1 in this set, then q should also be divided by p1. Now q minus p should also be divided by p1. But q minus p plus 1 minus p by p1 equals 1 by p1. But this is incorrect. 1 should not be divided by p1. It doesn't make sense. This theorem of arithmetic does not hold for this number. So our conclusion is p1 that we first assume here is not in the set. p1 should always lie on this position after p. Let's say px. Then there should always be another prime number px outside this range, this p1 to pn range. Now let's repeat our proof again. We repeat again p1, p2, p3 to pn. We put again px. Now this set is, let's say, finite. We repeat the same technique like we do first here, and the result is the same. There should always be another py prime number. We repeat again to infinity, then it proves that there are infinitely many primes. Is it cool? Thank you for watching my video.